Hello, I'm Rajaratnam. I've previously taken data course in my graduate program at UC Berkeley. So with that, let's get started with today's module. Today we're going to look at part one of convolutional neural network. And in part one, we're going to look at the motivation to use CNNs, uh, basic building blocks of CNN, and finally we're going to implement uh, CNN for image classification, a very simple and a basic implementation. So let's get started. Why do we need convolutional neural network? Why cannot we use the fully connected deep neural network that we looked at the previous module? It's basically because as the image size increases, the number of connections required per layer in increases a lot, and this will cause a lot of problem as the depth increases or the layers become sophisticated and the architecture becomes complex. So this is reduced by CNNs, which utilizes partial connections and weight sharing. For an example, a 200 by 200 pixel grayscale image would have 40,000 pixels, and if the first layer of a fully connected layer a network has just 500 neurons, then a total of 20 million connections exist for just the first layer. You can just imagine for multiple layers, this becomes very heavy. So that is why we are trying to use convolution. And what is convolution? A convolution is basically a function that represents what happens when one signal blends with another signal. Or we can imagine it in this way. Let's imagine one signal to be the image and another signal to be an information sieve or a filter. What would happen? What is the result if we apply the filter over the image? This is expressed through convolution operation. A convolution on matrix data will look something like this. A kernel is applied on data to the matrix, and after the operation, we get a feature map displayed in the green matrix. We'll delve deeper into this in the upcoming parts. So convolutional neural networks are based on the idea that local receptive fields in the visual cortex being responsible for specific stimuli to a limited region of the visual field. What do we mean by this is in the convolutional neural network, the initial layers are responsible to detect only a certain kind of features in the visual field. Let's say in an image, the initial layers can only detect lines, small directed lines, curves and shapes, very low level details. And as the layers keep adding or the depth increases, these features, low level features, are used to find and detect or form higher level features, eventually forming the most representative image of the picture that is being learned to recognize. That is the idea of convolutional neural network. And when you want to build a convolutional neural network, some of the basic building blocks are use of uh, padding, strides, filters in convolutional layers, and pooling layers. Now, what do we mean by strides? Stride is the unit movement of the kernel or the filter, and by default stride is equal to 1. And we can visualize stride as this lateral movement and the jump to the next row. So this is a case where stride is equal to 1. And for padding, we have two options, same and valid. Same will add zeros around the corners, around the sides, such that we can get the same output size as the input. And sometimes zeros can also be added in order to increase the output size compared to the input size. This is a case in which we can get this particular scenario. And if we use valid, we are not going to add any zeros, and the convolution occurs in this way. And based on the stride, information can be left out sometimes because the stride is too high. We use these parameters when we define the convolutional layers. Now let's look at convolution layers. So in convolution layers, when we talk about training of convolutional layers, the most important thing is the filters. What do these filters do? Is these filters act as informational sieve and try to form feature maps through training the CNN. So when we train the CNN, these filters have weights associated with them, and these are the parameters that are being learned when the CNN is trained on an input data set. So in this case, we are going to define 3 filters and look at the feature map if that filter is applied on the image. For that, let's look at an example. Let's use an image from a scalar node datasets, and for simplicity we'll use a grayscale image, and here we're going to apply define 3 filters, and we'll visualize how it results. So a vertical filter is used to detect just the vertical lines, and this is the filter when applied to the image. This is how the image looks like, feature map. And if we zoom in, we can see a vertical line kind of pattern. And if we use a horizontal, this is how a zoomed version looks like. And if we use a cross filter, this is how a zoomed version of a cross filter looks like. So the next important building block is pooling layers. Pooling layers are used to subsample the input image. This is extremely useful. Without losing too much detail, we can reduce the memory usage and the number of parameters and computational load associated with images or processing of images. So pooling layers do not have weights associated with them, unlike the filters. They are just there to reduce the size of the image or subsample, and they add small levels of invariance, to translation, which is very useful. Now we're going to look at 2 pooling layer types. One is max pooling. So in max pooling, when a kernel is applied, the maximum value inside that kernel is chosen as for the feature map. For an average pooling, the average value is chosen for that kernel. So let's visualize it. There you go. So as an input, the number of pixels is around 145,000 pixels, whereas when you apply max pooling, the same image is represented without losing too much of the information in just 36,000 pixels. That's the power of pooling layers. We can look at average pooling too. There you go. This is how average pooling also reduces the pixels required to represent the image. Now we're going to finally implement a baseline CNN for recognizing handwritten digits, also known as MNIST dataset. So as usual, we have a set of process to implement the CNN. First the data, then we're going to look at building the model, then we'll train it and then test it. So let's load the data. and let's visualize the data. It's a grayscale image of handwritten digits. So once we do that, we prepare the data set. We have the model. So for the model, what we're going to use is we're going to use LeanNet 5 architecture, one of the um primary CNN architectures, which was used for uh, detecting character or character recognition in financial institutions. So let's build it layer by layer. And the first layer, what we're trying to do is we're trying to use a convolutional layer with a kernel size of 5 and a stride of 1 and with 0 padding, that is padding equal to same, thus getting the same, yes, input and output size. This 32 by 32 is after applying zeros. Before applying zeros, it was 28 by 28. And once the first layer is done, we're going to go for the second layer where we're going to subsample it by using average pooling. Yes, and once average pooling is done, we are again going to use a convolutional layer and again a subsampling. Once this is done, what we're going to do is we're going to flatten it and connect it to two dense layers or two hidden layers or fully connected layers with 120 units and followed by 184 both with ReLU activation, rectified linear unit, and finally we want the output such that probability scores depicting um, the target vector. So we're going to specify 10 units and have softmax activation as the final dense layer. So this is a simple summary of the layers, and we can also look at it in this way. So imagine the number of connections that we actually thought of. So just look at it, we have 61,610 parameters to train for this simple model. Let's compile it. And yeah, let's train it. This will take a bit of time. Now we see that the 10 epochs of training is done and we get an accuracy of 98. Let's plot it. Well, we see that the plot. Let's just test it and visualize it. So we have the prediction 7, the ground truth of 7, the web edit is true and the ground truth is true, and so on. That's all for part 1.